Hey there, this is your stats chapter 9 practice exam, and I'm going to assume that you have it pulled up on a screen as a PDF, or you could print it out, but I'm assuming that you're looking at this. You can obtain a copy of this in straight from Canvas. Problem number one gives us a table and shows the number of satisfied in their work in a sample of working adults with a college education and without a college education. And they give us an alpha level of 0.05. And it looks like they want us to test the claim that the first population is larger than the second proportion. And we're looking for critical values. And because it's greater than, we're going to have a right tail. Zero. And this area here is 0.05. It's all there. And we're looking for this value. So this is, we can get that by doing inverse norm. So distribution, inverse norm. We need area to the left. We have area to the right. So I have to do my 1 minus trick. And that's giving us about 1.64. It does not say where to round it off. Now, they want to know, does the data provide sufficient evidence that the greater proportion? So we're going to actually run the test on this information here. And I'm going to do that by running stat test. This is a 2 proportion z-test. And it starts out 58 is my x1. N1 is 130. 50 is my x2. And 123 is here. And then we have greater than. Calculate. And we're just going to use the z value that we have here to determine what we need. And the test statistic, z, is about 0.637, which is way over here. So we are not in the critical zone, critical region. So we're going to fail to reject. The null hypothesis, and it doesn't ask us to put a whole explanation and so on. Number 2. This table shows number of smokers in a random sample of 500 adults between 20 and 24 years of age, one presumes. Oh, it says aged. And the number of smokers in a random sample, 450 adults aged between 25 and 29. And what they want us to test in this case, they give us an alpha of 0.1. The null hypothesis is going to be that the first proportion is equal to the second proportion. And the alternate hypothesis, they tell us they want us to test not equal to, which means we're going to get a 2-tail. Which tells us that we are going to be split up here, where half of this is here. The other half is here. Again, that's because of the not equal to. Now, they want the critical value or values. There's 2 in this case. We can find that by using inverse norm. And here, 0.05, it's area to the left. And we get negative 1.64. And to find this one, it's going to be the same as that one there, but I'll show you how to do it anyway. Over here, and now I have to do my 1 minus trick. 1 minus 0.05. Positive 1.64. So the critical values are plus and minus 1.64. And they want us to run the test as well. So this is again a 2 proportion z-test. Two-proportion z-test. And x sub 1, we have 110. And n sub 1 is the 500, and is always the larger number. X sub 2, 60. N sub 2 is 450. And this is not equal to, and it does all the work for us. It's beautiful. So our test statistic turns out to be z is about 3.19, which is way over here, meaning I'm in the critical zone, critical region. So we are going to reject the null hypothesis. And again, they don't ask us to do a full test on this one. We'll do some of those here in a bit. Number 3. So we're going to assume the samples are independent and randomly selected. So a researcher finds that 1,000 people who said they attend religious service at least once a week, 31 stopped to help someone. So let's write out what we have here as we're reading through the problem. So it looks like we have number 3. X sub 1 is 31. N sub 1 is 1,000. X sub 2 is 22. N sub 2 is 1,200. And we are given an alpha is 0.05. And I'm going to cheat this a little bit. It says, the very last sentence, it says, test the claim that the 2 proportions are equal. I'm going to say that they are not equal because I want the claim to be on the alternative hypothesis. So I'm slightly changing this. P sub 1 equals P sub 2. P sub 1 is not equal to P sub 2, making this the alternative, the claim. All right, so here we go. So this is going to be two-tail. I'm often asked by students, do we have to write the picture each time? I would like to see that. Also, visually, it's very helpful. So this is a split two-tail. So that means half of my alpha goes here. The other half goes here. And I'm now going to find my test statistic. So this is, again, is a 2 proportion z-test. And let's put our data in. 31 out of 1,000. 22 out of 1,200. We have not equal to, and calculate. Our test statistic is 1.929. That's a z. And my p-value is about 0.054, which is barely bigger than our alpha, which is 0.05. And I didn't find the critical values. Let's do that. So inverse norm 0.025. And so we're not here all day, negative 1.96. 1.96 are our critical values, and our test statistic is barely right there, just outside of the critical region. So we're going to fail to reject. Our null hypothesis. So there is not sufficient. Now this statement's going to be different than what you're going to see in the answer key because I changed the claim to be the not equal to. There's not sufficient evidence to support the claim. And what was the claim? The proportions are equal. Are not equal. So I've changed it again. If you look at the last sentence, equal. And you can always change it so that the claim is always on the alternative hypothesis, like on a test and stuff. All right, let's do number 4. See if I can squeeze number 4 down here. All right, so we have a random sample of 360. Now, it says 65 of them favored stricter gun laws. So my X sub 1 is actually going to be 360. 60 times 0.65. So 234. N sub 1 is the 360. X sub 2, I'm going to have to do the same thing. Of the 220, it says 60% favored stricter gun control laws. So that's 132. And N sub 2 is 220. They give us an alpha of 0.05. And to be clear, these are, so the ones are women. And these are the men. And let's see what our, it says test a claim that the proportion of women favoring stricter gun control, meaning they have a higher proportion, is higher than the proportion. So that's going to be P sub 1 is larger than P sub 2. All right, so this is going to be a right tail test. And that gets all of the alpha, the 0.05. And to get the critical value, we'll do inverse norm. I have to do the 1 minus. .64. All right, so let's get our test statistic and our p-value. Test statistic. And by converting this, the proportion into the x, the numerator, I can run the actual test here. Stat tests. This is a 2 proportion z-test. So 234 out of 360, 132 out of 220. This is a greater than. Here we go. I got that z is about 1.21, which is about, I'm exaggerating this a bit, about right there. P-value is about 0.1130, which is larger than my alpha. Significantly larger, actually. So our conclusion is fail to reject again. The null hypothesis. There is not sufficient evidence to support the claim that women favor stricter gun laws. Why did I misspell it? Stricter gun law. All right, moving on. Number 5. Construct an confidence interval between 2 proportions. Assume the samples are independent and that they have been randomly selected. So number 5, on a random sample, we have, notice they give us a percent here again. So for x of 1, we need to do 500 times 22%. N sub 1 is 500. X sub 2 is going to be 14% of 450. N sub 2 is 450. And I'll show you a little trick there in just a second. The one on 95, so our C level is at 95%. And the good news is that this is a 2 proportion Z interval. So now it's very common to do 2 proportion Z test. It's not a test. This is the interval. We want a confidence interval. 2 proportion Z interval. That's what we want right there. And watch what we can do. I can actually type in 500 times 0.22 directly into it. 500, 450 times 0.14. It won't accept a decimal, so you may have to round it off, and the answer will be slightly different, but we'll account for all of that. In 0.95, and watch this, you're done. It's really nice. So we end up with 0.3156, p sub 1 minus p sub 2, to 0.12844. All right, that's it. Number 6. The effectiveness of headache medicine. So we're checking to see if the 2 samples are independent or dependent on one another. The effectiveness of a headache medicine is tested by measuring the intensity of a headache in patients before and after a drug treatment. The data consists of before and after intensities for each patient. Are those independent or dependent? I would say those are definitely dependent, right? The effectiveness of a drug medicine that directly has to do with the intensity of a headache. So I'm going to say dependent. And for number 7, the effect of caffeine as an ingredient is tested with a sample of regular soda and another sample with decaffeinated soda. I would say that these two samples are very independent. You're going to get two very completely different results, and the two have nothing to do with one another. And let's scooch this up. Number 8. All right, now we're talking about population means. So we're no longer talking about proportions. Now, we're gonna, so an important sentence here is, it's in the second row, sort of in the middle to the right. It says, do not assume that the population standard deviations are equal. This means when it comes to pooling, we're gonna say no. No pooling in this case. And we'll see what we mean by that in just a second. So let's see what we have here. Looks like n equals 50 for both. And they give us an alpha of 0.02. And they want us to test. Let's see what they want us to test. Test the claim that the mean response time for company A is the same. So I'm going to say is not the same. Again, I'm changing it here. So that the claim is on the alternative hypothesis. And it looks like we're splitting up. There's going to be a two-tail because of the not equal to. And because we know nothing about their standard deviations, population standard deviations, this is definitely a two-sample t-test. So this is a two-sample t-test for a test statistic. Before we do that, though, n in this case for both, n sub 1 equals n sub 2, which is 50, which means our degrees of freedom is going to be 49. So I'm going to have to use inverse t in this case. So inverse t. Now, if you have an older calculator, a TI-30 maybe, you may not have inverse t. You'll have to look it up using the table, the t table. So inverse t. Now the area is always area to the left, 0.01 in this case. Degrees of freedom is 49. Negative 2.40. And I could run it again. It would give me a positive 2.40. So here are my critical values. And I'm now going to run my test statistic. So this is a two-sample t-test. Two-sample t-test. And they give us the first mean is 7.6. Looking at the data from problem 8. Standard deviation is 1.4. N is 50. X2 bar is 6.9. Standard deviation is 1.7. And N sub 2 is 50. Now this next part here is going to be not equal to. But this one here, is it pooled? The answer is no. And if you go back to the problem, it says, do not assume that the population standard deviations are equal. That means we are not pooling the standard deviations or the data. And calculate. So it looks like T is at 2.248, and our p-value is 0.027, we'll say. Now that is larger than my alpha, which is 0.02. So, and we can see 2.248 is definitely smaller than our, we can see 2.248, pardon me, is here. I'm exaggerating this. So our conclusion is fail to reject the null hypothesis. So to save time, I'm only going to write part of it. There is not sufficient evidence to support the claim that, and so on and so on. Trying to make this video as short as we can. So you would just restate the claim. There's not sufficient evidence to support the claim that. All right, number 9. You have to write it out though, unfortunately. Number 9, we have a confidence interval between two population means. This is going to be a two-sample T interval. And we have our information here. Again, we're going to assume that the two samples are independent, and we're not going to assume that the population standard deviations are equal, so the pooling is going to be turned off. And so here we go. The researcher was interested in comparing the resting pulse rates of people who exercise regularly and those that don't. She obtained sample size, well, the data is all there. They want to construct a 95% confidence interval for the difference of the two means. That's it. And this is very, very simple. We're going to go here and we're going to go to stat tests, and we're going to go down to two sample. Now be careful, it's not a two sample t-test. This is an interval, two sample t-interval. Two sample t-interval, there it is. Your numbering may be different than mine, depending on your calculator. And our first X bar is 72.9. Our first standard deviation is 10.9, and N is 16. Our next one is 69.4. Standard deviation is 8.2. Sample size of 12. Confidence level they give us is 0.95. We are not pooling it. So if no is not highlighted, you would just hit enter and it would highlight it. And calculate. We're done. So negative 3.92. $10.92. And you can see 0 is between there. All right, that was 9. On to 10. All right, in this case, they are telling us that we're going to assume that the population standard deviations are equal, so we can turn on the pooling. So let's run a test. Let's make sure we are. Okay. All right, so they want us to use a 0.02 significance level. That company A differs from the mean response time of company B. So our null hypothesis So we get mu sub 1 equals mu sub 2, and mu sub 1 is not equal to mu sub 2. So we're going to get a two-tail. And we're going to get 0.01, 0.01. Now, n is the same for both. So our degrees of freedom is 49. So let's calculate our critical values. Distribution, inverse T. Again, if you don't have inverse T, you'll have to use the table. Area 0.01, degrees of freedom 49. Oh, that's the same one above. So the critical values don't change, but the test statistic will, because we're pooling in this case. Negative 2.40 and 2.40. And our test statistic, again, I'm going to run a two-sample t-test. So two-sample t-test. So our test statistic is going to be calculated here. So this is stat two-sample t-test is here. And we have our data, and I'm looking at back here, meaning our PDF 7.6, 1.4, 50, and mean second one for company B is 6.9, standard deviation of 1.7 and 50. This is a not equal to. In this case, we are pooling. Because once again, if you look at the bold print on that in the middle, it says also assume the population standard deviations are equal. So that means that we are pooling the sample variances. And calculate. So T, 2.248. Notice it looks the same. And the reason is because n is so high. When that happens, they start getting closer and closer to each other. P-value is 0.0268, which is larger than our alpha. So we're going to, once again, fail to reject. So this, again, goes right here. So we're going to fail to reject. H naught. So there is not sufficient evidence to support the claim that the two different companies are different. Again, so we can speed this along. You can write your own sentence. Moving on to problem 11. Now, problem 11, we're finding the difference between these two dependent sets. And I have loaded already into here list 1 and list 2. So list 1, you can see, is the 236. The list 2 is the 194. You may need to pause this video so that you can put the data in. But I'm going to show you a little trick. If I go up here and I go L1, let me show you how I'm going to do that. So I go up to where it says L3, and I go to second L1 minus second L2 and throw it in there. It takes the difference. That minus that is there. That minus that is there. That minus that is there. Isn't that cool? Gotta love that. And now we're going to run the information on problem on list 3 as far as the data goes. Now, what makes it very nice is we now have our differences, a list of differences, which is in list 3. And now I can just run a 1vars stat on list 3, and there's no frequency list in this case. Now, list 3 is above the number 3. So I'm going to hit second 3, and that gives me list 3. And then I calculate. And actually, D bar is X bar. So D bar in this case is the 30.143. It's quite nice. Moving on to number 12, we're doing a full-on test here. So through the magic of recording stuff, I actually went in and I entered in all the data for problem 12 into list 1 and list 2 again, and I'll show you that here in a second. Let's start with 12. And our null hypothesis in this case is the mean difference. We're going to assume that there is no difference, that it's 0. And they just want the value of the appropriate test statistic. So we're not running a full test yet, which is fine. And what is the value of the test statistic? Yeah. So it's effective. Actually, this isn't true. This will be here. If it's effective in helping them lose weight, then it should be positive. Meaning they start out at 168 pounds minus 162. That mean should be positive. It should be high if they're losing weight. Now you'll notice that makes it one tail. And they don't even want to know. They just want the test statistic. That's fine. So I'm going to do this. Once again, I paused it so that I could enter in list 1 and list 2, this new data. I'm going to do my little trick again. I'm going to go up to L3 and I'm going to go L1 minus L2. Bam, there it is. And now I'm going to run a t-test on list 3. And for this, I have data. And this is 0. And I need to change it to list 3. That's second 3. That changes it to list 3. We have a larger than situation here. And to calculate. So you can see our test statistic is T is equal to 3.144. There it is. Number 13, I'm going to go ahead and enter all that data in again. All right, so I have entered the data into this here. And for number 13, they want us to find a confidence interval for the mean differences of D in a population paired. And these are 10 different families are tested for the number of gallons of water a day they use before and after watching a conservation video. Notice we're constructing a 90% confidence interval. And I'm going to go ahead and do my little trick again. Stat. So I put list 1 and list 2. And for list 3, I'm going to do L1 minus L2. That finds the differences for all of that. And even more nice, I can go in, and this is going to be just a regular t interval based on the data in list 3, so it keeps the L sub 3 there for me. Frequency is just 1. And the confidence level is 0.9 for this one. That says go. That's it. Does everything for you. So we end up with 1.7595 and 7.84. 405. That's the whole thing. Pretty nice, I'd say. All right, number 14. I'm going to take a minute, pause it again so that I can put the data in. All right, so I added those in there, and this is a full-on test that we're going to be running here. So in this case, they want to know if this diet is effective, meaning they're losing weight. The assumption is always that nothing happens, that there is no change. That's the default assumption. And if they lose weight, then it should end up being positive. Now note they give us an alpha. In this case, alpha is 0.01. And n in this case is 7. Now I know there's 14 numbers there, but we're pairing each of those numbers to make one sample. So n is 7, that means degrees of freedom is 6. And this is a right-tailed test. And this is going to be a t-test, so I need to do inverse t. And because it's area to the left, I need to do 1 minus. Degrees of freedom in this case is 6. Here's our critical value. All right, and again, I paused it earlier so that I could enter the data in. So let's find our test statistic and our p-value. And we're going to be running a 2 sample t-test. So stat 2. I'm sorry, this is a 1 sample now. Let me get to it. A 1 sample. And we need to do the trick first. So here is the first list and the second list. And I'm going to go here and do L1 minus L2. And I'm going to run a t-test. And I forgot what the TI, they just call it a t-test. So it is a 1 sample t-test, but you're not going to find that as one of these. So this is just a t-test. There we go. And 0 still. List 3, we're good there. Frequency is 1, and this is larger than, so we're good to go. So here is our t approximation, 1.95, which I'm going to really exaggerate. Goes here for the p-value of 0.049, which is way bigger than our alpha. So we once again are going to fail to reject. And this means that there is not sufficient, I'll write this one out, sufficient evidence to support the claim that works. Doesn't mean that it doesn't work, it's just there isn't enough evidence to support a claim saying that it does work. And the last one for today, number 15. And for the last one, I'm going to pause it again so I can put the data in. So I'm realizing that this data is the same data as the number 13. So maybe next time I'll reorder them so that I don't have to do it twice. All right, so for number 15, they say we have 10 different families, so n is 10, which means our degrees of freedom is going to be 9. And the amount of gallons of water they use before and after viewing a conservation video, our alpha, 0.05. And they claim that the mean is the same before and after the viewing. I'm going to say that the mean is not the same. So that, again, my null hypothesis is that they're the same. My alternative hypothesis is that they are not the same. All right. So we have a not equal to, so we have a two-tail. And let's get some critical values here. Inverse t, and to be clear, degrees of freedom is 9 in this case. So 0.05, degrees of freedom is 9. Negative 1.833. And this is going to be 1.833. So there are our critical values. I'm now going to, so here are the two rows that you see in 15. This is the before and the after. And fancy little trick again, L1 minus L2. And I'm going to run a t-test. On list 3 again. In this case, the only difference is the not equal to. So it looks like our test statistic, T, is 2.89, which is way over here. So we are in the critical zone, critical region. And our p-value, 0.0178, which is less than our alpha. Oh, I was rushing. This should be 2.5. 2.5, and I'll fix these. So let's find our critical values again. Well, 0.025. Negative 2.26 and 2.26. It's still in the zone, so that doesn't change. And because our alpha is 0.05, you can see this is definitely less in this case. So what does that tell us? How do we interpret that? This means that we are going to reject. So reject the null hypothesis. So there is sufficient evidence to support the claim that there's a difference before and after. Before and after watching the video. And there's your practice test. Thanks. and good luck on your test.